Hello and welcome. So, we have reached almost the end of this course. So, in the last class, we we looked at the electronic states of naphthalene molecule. So, what we did, we took the SLCs that were formed out of the p pi orbitals on the carbon atoms of naphthalene molecule, and filled it up with the electrons using Hund's rule and using Pauli's exclusion principle, and we found the symmetries of the individual electrons in those molecular orbitals, and then we form the different excited states by putting one or electron taking from one of the filled orbital to one of the vacant orbitals. So, we learned how to form the find the symmetry of the electronic states. So, what we got, we formed three different excited states. So, they were the ground state was a totally symmetric. It transforms as the totally symmetric irreducible representation, while the the lowest excited state that was B2U symmetry. So, and also there are we looked at two other excited states, both of that. So, two excited states, both of which had B3U symmetry, and we also looked at their energies, right. So, for this B2U state, we found the energy to be 1.236 in unit of beta, and for the other two excited states which had B3U symmetry, we found the energy to be 1.618. So, for both the B3U, so we had two excited state having B3U symmetry, and both of them we calculated, we found this energy by using Huckel's approximation and solving the secular determinant and secular equations. We found these energies. Now, one important part in this case that we will be talking about today. Though this is the value that we are getting by calculation, and we also got the related selection rules for the transitions from the ground state A1G to B2U and these two B3U states, and we found whether the transition was allowed or disallowed. Now, when someone looks at the energies of these states, these three states, surprisingly it is found that this there are two different energies actually for these two states having B3U symmetries. So, there is something else going on. Okay. So, like I have A1G to B2U and A1G to B3U, A1G to B3U, and this both of these should have the same energy of transition, but experimentally one finds that they have actually different energies. And as a matter of fact, the energies of B2U is actually in between the energies of two B3U states. That is quite surprising. So, why is it so? That is what we will look at. Okay. So, in a nutshell, if I tell the reason is known as configuration interaction. So, reason is configuration interaction. So, what is that? That we will look at. So, whenever we wanted to find out the energies of any given state, what we did, we looked at the energy integral. So, the energy integral that we looked at was something like this. So, the Hamiltonian and this, and what we said about the value of this integral. So far we have been talking about that this particular integral may have a non-zero value if this psi 1 and psi 2 have the same symmetry. That means, if psi 1 and psi 2 belongs to the same irreducible representation of the point group, because this Hamiltonian being the energy operator, it is totally symmetric. So, it transforms as the totally symmetric irreducible representation. So, therefore, this psi 1 and psi 2 must be having same symmetry, otherwise they will be 0. Now, what we have in the present case, that two excited state belonging to the same symmetry B3U, right. So, can we have some this particular situation, we can say that even though two states belonging to the same energy, they may lead this integral to have a 0 value. Okay. So, this is a special case. So, this is something like which is kind of accidental. Okay. Now, what may happen here is that two states having same symmetry, that is B3U, they may interact with each other, and while interacting, after interaction, they get split up. So, when you get this new state, so you have two B3U states, they are at the same energy. Okay, calculated, we found that they are of same energy and they are of same symmetry. Now, there is some interaction is going on, and after that they are forming two different states which are different in their energies, and this energy gap is quite substantial. So, that this other energy state B2U, that lies somewhere in between. Okay. So, if we in this case, actually the resultant new states, they cannot be expressed as the purely one of the B3U energy state. None of these new states can be expressed as the pure B3U state. So, there therefore, we have to assume that there is some kind of mixing, and due to this mixing you get a splitting. So, in that case, we can describe this mixing and splitting by second order secular equation. So, the mixing and the following splitting can be described by a second order secular equation. We have seen this secular equation earlier, and we solved them and found the energies for the very same naphthalene molecule. So, how will this look like? It will look like it is very similar to the other secular equation that we have formed. Now, here this H12 is of particular interest, because this orthogonal element, they give you the interaction terms, right. So, this H12 I can now express in this following way. So, if I say I take psi B3U and the Hamiltonian, and then I get a new psi B3U, I call it as psi B3U prime. Okay. integration over d tau. So, in such a case, what we have is, two different states with two different energies. And what are their energies? So, the energy levels that has like E0 plus H12, and you have E0 minus H12, right, that we have to have. So, this entire situation is pretty much analogous to the occurrence of a 2 by 2 determinantal equation, right, for the energies of two individual orbitals of same symmetry. Now, actually in practice it is bit different. It is difficult to compute the magnitude of this H1 to this particular integral, because it involves actually the electron repulsion, and which is always difficult to measure. So, if I want to show how actually this states of same symmetry and same energy they mix and split diagrammatically, then I can show it like the following way. So, I had to start with, say, this is my B2U symmetry, and then I have two states with B3U. Both of them have B3U symmetry. So, this means that they have same energies. Okay. So, just for clarity, we are drawing in such a way that they are slightly separated, but you remember that both of them have same energy to start with. So, this B2U, this state is not interacting with any other state. So, therefore, that remains as such. Okay. While this guy, both of them will mix, and then they will form states which are having energies completely different from the original energies of individual B3U states. Okay. So, this is my new picture after this interaction and mixing and splitting. Okay. So, in its most general form, this configuration interaction, it involves two states having same symmetry. Now, always if you have this kind of situation, what you have end up what you have is you have a splitted energy level, and it can not only happen in case of electronic state. You can have the same situation in case of vibrational transitions also involving vibrational states. Now, this is not we are not going to talk about these things in details, but I will just mention that in case of vibrational transition involving vibrational states, such mixing, or rather if I say configuration interaction, that leads to a very exotic phenomena. This is called Fermi resonance. And because of this kind of configuration interaction in case of vibrational transitions, a very unique thing happens, that even a very a mode which is very weak, such as like combination mode, we mentioned about that, or overtone. This combination or overtone bands can actually become much more intense by borrowing intensity or oscillator strength from an allowed transition, okay, or say rather I should say from a pure fundamental transitions. So, here whatever we talked here so far is to tell you that we use this energy integrals to say find out whatever the energies of this uh, on any given particular state. And also we use this type of integral and use the symmetry or impose the symmetry conditions in such a way that we said always that two states which are involved in having transition between them must belong to the same symmetry as that of the operator, correct. So in this particular, when we looked at today, is opposite. Like in certain cases, when you have the same symmetries of these two states, and you should have an allowed transition in such case. I mean, like you should have a integral that should not vanish. Now there, in some cases, you may end up actually getting a complete different picture because of the interaction of those states having same symmetry and same energy. This interaction is known as configuration interaction, which is very much valid in case of electronic and other like vibrational energy states. And one important aspect is you you use this valence bond theory in while talking about the molecular resonance and all these things, and you use this resonance energy. Okay, so by which uh, you talk about the stabilization, meaning the resonance stabilization. So that actually uses this configuration interaction in a particular way. So with this we will conclude this session. So I hope we could convey the basic notion of the symmetry aspects of various different types of transitions in a given molecule, vibration and electronic, and we learned how to how to find out the symmetries of these various states, be it in the case of normal mode of vibration or be in the electronic states of a given molecule. And then we found out the symmetry selection rules, symmetry adapter selection rules, and also in today's class we learnt about the special cases when even having two states with same symmetry may end up giving a different result because of the mixing of the two states. So in the next class we will come with the summary of the total the course that we had so far. So we will try to summarize whatever we learned and try to give you recapitulation of whatever the lessons that we had so far. So thank you very much.